In today's video, we get to explore probability and how integrals actually help us with probability. If you remember, in our previous video, we talked about some of the more basic statistic stuffs like mean and standard deviation. You're going to see those again today as we go through this, and that's why I wanted to review those with you guys. Now, this section is all about probability density functions. What is a probability density function? A probability density function is a function that expresses how likely an event is. So if you think about it as an equation, if you plug in a certain number, the output is going to be how likely that specific outcome is. So here's an example for you. So an example of one is the function, here I'm going to be p of x, actually p of t, because our independent variable in this case is time, is equal to 0.23 e to the negative 0.23 t. Okay, and this is my probability density function for the average wait time, or not average, but the amount of time you have to wait on a 911 call. So theoretically, I can plug in a value like 5 seconds, and it's going to give me the probability that I'm going to wait 5 seconds for my 911 call. Well, where do integrals come into this? Let's say I wanted to ask the question, what is the likelihood or the probability that my wait time will be under 10 seconds? So this is a more complicated question because this is a whole range of values. This is looking at what's the probability that if I wait on the line for a 911 call, it's anywhere under 10 seconds. That could be 5 seconds, that could be 3 seconds, that could be 2.5 seconds. There's so many different possibilities here, and which makes this more complicated than just plugging a number into my function. So if I actually graph this, let's see what this looks like. So the graph of this function is just an exponential decay function, so it looks like this. And if I think about this as my 10-second spot, I'm looking for what's the probability that my result is less than 10 seconds. Well, that could be right here, 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 so on and so forth, to the point where I end up just looking at this entire area. I end up with the area under a curve, which is exactly what integrals are used for. So it turns out to calculate this value, I can just do the integral from 0 to 10 of 0.23 e to the negative 0.23 t dt. And that'll give me my probability. In fact, if you actually plug this into a calculator, or this is actually something, you guys could solve this on your own. This is not a complicated integral to figure out. I get 0.8997, about. It's approximate. Notice, what does this answer look like? It's a number less than 1. That's because this answer is a probability. It's a percent chance. So what is this telling me? This is telling me there's an 89.97% chance that my wait time will be less than 10 seconds. Will be 10 seconds or less. 10 seconds or less. So almost 90% chance that you're going to wait 10 seconds or less. So now that we understand how probability density functions work, we can actually understand there's one major characteristic that all probability density functions have. For our probability function, think about what would the domain be? What are my possible wait times? Well, for sure, my wait time has to be greater than 0. But am I bounded really by anything else? No. So my possible values here are 0 to infinity. So let me actually write that. My domain here, right, domain is all possible x values. My domain is 0 to infinity. Well, probability density functions have this property that if you integrate it over its entire domain, so in my case, I'm integrating all the way from 0 all the way to positive infinity. Notice that gives us an improper integral, okay? What do you think is going to happen? What's the probability that my result falls within the possible domain? Well, my probability is there's a 100% chance, correct? So sure enough, if I integrate this from 0 to infinity, I should get 1, which of course corresponds to 100%. So this is a property that all probability density functions have. If you integrate them over their entire domain, they should equal 1. Okay, so there's our basic review of probability density functions. And so let's move on to what we're going to actually discuss in 5.5. If you want to learn more about probability density functions, take a look at 5.4. You can find it in, just on Pearson, just in your book, but we're not going to do an assignment over that section. Okay, well, it turns out I can also, using an integral, I can also calculate the expected value of a probability density function. What does that mean? Well, let's keep going with my example. And let's ask this question. How long should I expect to wait when I dial 911? Pretty much, what's my expected wait time? Okay. Well, what does that kind of sound like? It almost kind of sounds like an average wait time, right? Wouldn't the average wait time be the expected wait time? And that's absolutely correct. But how do I find an average here? I don't have data values. I don't have a list of all the wait times for all the calls over the last month or anything like that. All I have is this probability density function. Well, it turns out I can calculate this using my probability density function and using an integral. What I'm going to do is I'm going to integrate it over its entire domain. I'm going to integrate the function just like I did before. But once again, if I just integrate this, what am I going to get? I'm going to get out 1, because all that's saying is that there's a 100% chance that your wait time is going to be somewhere within this possible interval. But what I'm going to do to actually calculate this expected value is I'm going to multiply my function by my independent variable. So if you're working with x, it would just be x times your function. Since I'm working with t, it's t times my function. Okay? And then I'm going to integrate that. This is, of course, a little bit more complicated of an integral. It requires integration by parts, but it's still possible. We know how to do something like this. And when I do that, I get about 4.34. So this is what's considered my expected value. We write it capital E of x. What does that mean? That means if I call 911, I should expect to wait about a little over 4 seconds. And it turns out this ends up being my average wait time. So expected value and average are the same. So let's generalize this. If you're working with any function, any probability density function, if P of x is a probability density function over the interval a to b, okay? So that's the interval that it's defined over. In our case, it was 0 to infinity, but in this arbitrary case, let's just call it a to b, then the expected value of your probability density function is this integral from a to b of x times my function, times my probability density function. Take that integral. Most of the problems on your homework, your probability density function is going to be some sort of power function, which will make life a little bit easier for you. Well, that gives me my average, but the other very useful thing in statistics is knowing how spread out my data is, and that corresponds to the standard deviation. Well, it turns out I can use integrals to find that standard deviation as well. But this one gets a little bit more tricky. Okay. Recall that the standard deviation is just the square root of the variance. Okay. You'll see us write it like this. The sigma represents my standard deviation, and sigma squared represents your variance. Okay. So if I want to find standard deviation, I can actually find it by finding my variance first. Well, it turns out you can find variance by calculating the integral from a to b. And I'm going to do something similar that like I did with the expected value, except I'm going to, instead of multiplying by x, I'm going to multiply the probability density function by x squared. So I'm going to take that integral and subtract your expected value squared. And remember that I can calculate this expected value just by doing the integral from a to b of x times your probability density function. But once I'm done with that, I'll square that value. Okay? So let's look at my specific situation. Let's go back to my 911 calls. Okay? If I want to calculate that variance, I'm going to take the integral from 0 to infinity of t squared times 0.23 e to the negative 0.23 t dt minus, well, once again, remember, I already calculated the expected value. I know what that is. My expected value is about 4.34. And I'm going to square that. This integral is even more complicated than my last time, but I still know how to do it. This actually requires tabular integration by parts because I'm going to use integration by parts twice. Still possible, though. Okay, that's still one that we can actually crank out on our own. Okay, and I get about 37.8072, but then I have to subtract my mean or my expected value squared, and I end up with 18.9036. So there's my variance. So, and then to find my standard deviation, all I have to do, right? Standard deviation is just the square root of my variance. And I get about 4.3478. So using integrals, I was able to calculate both the average and the variance of a probability density function. So go ahead and pause this video and you can try some of the problems on your homework, and then we're going to move on to normal distribution functions. The most common type of probability density function that we'll work with is called the normal distribution. Why? Because this is how data is normally distributed in nature. So if I look at the shape of this density function, think about human height. If you think about like the average height of a person, most of us are all right around the average height. The taller you get, the more rare that is. The shorter you get, the more rare that is. And so it makes this what we call a bell curve, where it's really close to zero on the edges, and then it comes up with this mound, right? That's centered. You'll notice it's centered at the mean. It's centered at the mean. Okay. And what's nice about the normal distribution is it's symmetric. Okay. It's the same on both sides of that dividing line. What's the dividing line? Is your mean, is your average value. Your average value is going to be your dividing line. Okay, so it's symmetric. The other nice thing is that the domain covers all real numbers. So negative infinity to positive infinity. So that's nice. I don't have to worry about limiting my domain. What's not nice about this function is if you actually write it, it's 1 over the standard deviation times the square root of 2 pi times e to the negative 1/2 times x minus the average over the standard deviation squared. Ugh. Guess what? That's not a function you can actually integrate. Okay? It's very, very complicated to integrate, and it requires a calculator. So how is this helpful then? Well, we do have powerful calculators that can do that sort of computation, and you'll actually see on your homework, we're going to provide you with what this is called a z-score table. And to put it simply, the z-score table is all the integration done for you. All the integration's done for you. Okay. So what is a z-score then? That's something new we haven't talked about. What is a z-score? You'll notice that's what's up here in the top left corner is a z-score. Well, the normal distribution really depends on two things. It depends on it depends on what your mean is, of course, because that's what it's going to be symmetric around. And it also depends on your standard deviation. The smaller your standard deviation, the steeper your mound. You get something like this. The bigger your standard deviation, the more gradual your mound. You get something like this. Okay? So, a normal distribution depends on those two things. Mean and standard deviation. And what a z-score is the z-score tells you how many standard deviations away a data value is from the average or the mean. Okay, so take a look at some of these z-scores. So you'll notice you've got the ones digit and the tenths digit on this left side, and then the hundredths digit on this right side. So let's say my z-score was, 1.57. Okay, I'd come down here, find 1.5, and then come all the way out here to the 0.07. And I'd end up right here. And I'm going to explain what this number is in a little bit, but there's my z-score, 1.57. What does that mean? That means I'm looking at the data value that's 1.57 standard deviations away from my mean value. So what is this value? Well, if I come back up here to my graph of my standard deviation, of my normal distribution. Let me redraw it because I drew so much other stuff on top of it. Okay, if I have that normal distribution curve, what that number is the area under the curve from the mean, aka from 0, right? 0 standard deviations away from the mean, to my z-score of 1.57. If I look at the area under the curve of that, that's what this number is, 0.4418. So what does that tell me? There's a 44% chance that my value is going to be between the mean and 1.57 standard deviations away from that mean. Okay, so there's a 44% chance that your value is in between the z-scores of 0 and 1.57. That's how you read this z-score table. So let's try another example just to get this cemented in our heads. What is the probability that a z-score lies between 0.91 and 1.54? Okay. Well, let's find those two z-scores on my z-score table. Okay. If I start with 0.91, I'm going to go to 0.9, and then my hundredths place is just 1, so I'm going to find my data value. So I get 0.3186. Is that my answer? No, recall that represents, if I come back over here to my normal distribution, that 31.86% represents the probability of the z-score being between 0 and 0.91. This z-score table will always give you the area between 0 and that z-score. Okay? And so I would also need to find it for 1.54. So 1.5 and then a hundredths place of 4. That leaves me with this one. So I get 0.4382. So that means if I find this area from 0 to 1.54, I get 0.4382. But we want the region in between these two z-scores. How can I find that? Well, it turns out I can find that by just subtracting, right? I can take my red area and subtract away the blue area in order to get the area that I'm looking for. So I can just take my larger area from my larger z-score and subtract that smaller area from my smaller z-score. And I get 0.1196, or 11.96% chance. So there's a almost 12% chance that your z-score is going to end up between those two. Now you'll notice we haven't seen any negative z-scores yet. How do negative z-scores work? So let's say I asked you this question. What's the probability? Oh, in fact, I forgot that. That's how we mark probability. So what's the probability that my z-score is less than a negative? So yes, negative z-scores are a thing. Negative z-scores just mean that I'm working on this side. So this would be like negative 2.05 is on this side of the mean, on the left side of the mean. So what am I really looking for? I'm looking for this area. Well, my z-score table doesn't have any negative values on it, so how am I supposed to do this? Well, the key here is remembering that the normal distribution is symmetric, which means all of these same areas still apply for negative values as well. So if I go ahead and find the z-score for just positive 2.05, let's see what we get. 2.0, and then I'm going to go to my hundredths place of 5, and I get this, 0.4798. What does that area represent? Is that my answer? Well, it turns out it's not, because remember, this z-score table is always in reference to the mean. So what I just found is I found the area between negative 2.05 and 0. I found that area. That area is about 0.4798, or almost 48%. But I want to know what's the probability that it's less than negative 2.5. What's this area? The key to figuring this out is recognizing that because my normal distribution is symmetric, that means you will always have 50% of your data on either side. So I'm going to have 50% on this side and 50% on this side. Okay? So if I know that 50% is on this left side, but this red area represents almost 48%, what can I do? I can just subtract this area from 50. I can do 0.50, right? 50% minus that area, and I get 0.0202. And this represents my solution. There's a 2.02% chance that my z-score is less than negative 2.05. So that takes care of finding probabilities just based off of z-scores. Bottom line, what's going to help you the most is to draw one of these pictures just to help you. I know this is kind of crazy because I've used the same picture for multiple problems. But whenever you look at one of these standard distribution problems, go ahead and draw yourself a picture to kind of help you out. So that you can kind of see, what do I need to do? Do I need to subtract these two areas? Do I need to find the difference between 50% and this? Use a picture to help you out. How does this relate to actual data? Okay. Well, it all boils down to if you want to use this table, your data needs to be in terms of z-scores. Okay. And once again, what is a z-score? A z-score is how many standard deviations a data value is from the mean. So let's say I gave you a situation. Okay. You work at a restaurant and you get an average of 220 orders a day. But of course, that varies. It's not always 220 orders a day. And you find that you have a standard deviation of 20. You by yourself can only handle so much. And so you guys have found that when orders exceed 252, more help is needed. So this begs the question, what is the probability that you get more than 252 orders? Now, if I try and put 252 into the z-score table, you're not going to find it anywhere. I need to get this 252 in terms of a z-score. Well, how far away is this from my mean? And not just how far away, right? I mean, I can calculate that fairly easily. 252, if I just subtract my mean, this tells me how far away it is from my mean. But the z-score isn't just how far away it is, it's how many standard deviations away it is. So, how many standard deviations is 32? Well, I can find that fairly simply by just taking this number and dividing it by the standard deviation. And I get 1.6. This tells me I'm 1.6 standard deviations away. This is my z-score. Okay? So, in general, to generalize this, your z-score is just your data value minus the mean. That might get you a negative value, and that's okay. What does a negative value mean? Negative value just means that your data value is smaller than the mean. And then you divide that by the standard deviation. So that's your z-score formula. Once I have that z-score formula, then I can go ahead and use my z-score table. Okay? So if I come up here to 1.6, what's my hundredths place? My hundredths place is just 0, and so I get this value, 0.4452. Okay, this gives me a z-score of 0.4452. Okay, but be careful. Remember, this always represents the area between 0 and that specific z-score. And that's not what I'm asking, right? I'm not asking what's the probability that you get between 220 and 252 orders, because that's what this would represent. Remember, a z-score of 0 represents the mean. I'm wondering what's the probability that my z-score ends up being greater than 1.6. Well, this ends up being a similar example to the one that we just talked about here. Okay. I'm going to draw a picture to help us. Here's 1.6. I want this area. What do? I take 50% and I subtract whatever this area is, which I know what that area is, right? That's what this value means. I'm going to subtract 44.55%. Sorry, typo, this should be a 2. What do I get when I subtract those two? I get 0.0548. 5.48% of the time, my orders exceed 252. Now let's talk about percentiles. That's something that you guys have probably heard of before. 10th percentile, 50th percentile. What does that actually mean? Well, the reason why we're going to talk about this is because percentiles are also based off of the normal distribution curve. So what do they mean? So let's start with a very simple example. Let's start with the 50th percentile. What does the 50th percentile mean? Notice percentiles are in terms of percentages, which means I'm actually talking about the area under the curve. So if I'm talking about the 50th percentile, I'm talking about where do I stop so that I end up with 50% of my area. Well, we've actually already answered this question. We answered this question based off the fact that the normal distribution is symmetric. So where am I going to stop so that my function ends up being at 50% of my data? So that I'm stopping at 50% of my data? Well, I'm going to stop at the mean. So it turns out that your 50th percentile represents a z-score of 0. Right? Remember, z-scores is how far are you away from the mean, and if I'm going 50% of my data, then I'm exactly at the mean. I am 0 standard deviations away from the mean. Okay? But what if I wanted to ask you something not quite as simple, right? Take the 70th percentile. what z-score corresponds to the 70th percentile? Well, that means I want to keep going. I'm going to keep going until I hit 70% of my data. Ooh, sorry, I shouldn't put that down there because that makes it seem like a z-score. I'm solving for what that z-score is. What is this z-score? So that this area is 70%. Well, we already said that to get to the mean, this is 50%. What does that mean about this region right here? If the left side of the mean takes care of 50% of my data, and I want to get to a total of 70%, then this red area represents 20% of my data. Why am I doing this? Because if I want to be able to use this z-score table, I have to have it in terms of my area from 0, right? The z-score is always in terms of how far away is it from the mean, okay? So 20% of my data is to the right of the center or the mean. So let's come back to my table. If I know 20%, notice I don't know the z-score, so I'm not going to look at the edges of my table. I'm going to look right smack dab in the middle of my table to find an area of 20%. So let's look. Right around here, it skips over 20%. So I go from 19.85% to 20.19%. Which one's closer? Well, closer is 0.195. That one's the closer one. This one's closer to 0.2. And so this is the z-score I'm going to use. I'm going to use a z-score of 0.52. So that's the z-score that corresponds to my 70th percentile. So notice, I didn't go search through my table for 70%. You will never find 70% of your data on this table. You will never find 0.7 because this table is always starting at 0. It's not starting all the way at the left-hand side. It's starting at 0. Well, what about the 10th percentile? What is this looking for? Well, here, let me draw another standard distribution to help me out. Once again, that's my biggest advice for this section is just keep drawing these normal distribution curves. And what it's asking for is how far do I go? What z-score do I stop at where I'm at 10% of my data? Oops, sorry, I did it again. I shouldn't write that down there because that's going to represent my z-score. How far do I go before I stop so that I reach 10% of my total area? So, should I come up here and just look for 10%? Remember, this table is always in terms of your distance from, your distance from 0. So if I come back down to my picture, how far away am I from 0? I'm not 10% away from 0. I'm actually 40% away from 0. How do I get 40%? That's this area. That's how far away I am from 0. If I've only reached 10% of my area on this side, then that means the rest is 40%. Why? Because 50% of your data will always be on the left side of the mean. If I do 50% minus 10%, that gives me this area. And that's my area between my z-score and 0. So that's what I'm going to look for. Let's look for 40%. Okay. 40%, 40%, 40%, I end up here, either 0.3997 and 0.4015. Which one's closer? This one's closer. So I'm going to take that z-score, 1.28. Do have to be careful here. I don't want to leave it as 1.28 because that represents my z-score way over here. This is 1.28. So what z-score is this? This is negative 1.28 because it's on the left side of your mean. I know that was a lot today, so if you have any questions, please reach out and let me know. But good luck with the homework, and I'll see you in the next video.